everyone, welcome to part 3 of chapter 3. Last time we talked all about ionic compounds and how ionic compounds are typically between a metal and a non-metal. These differences of charges, right? This positively charged cation, which is typically a metal, and this negatively charged anion, which is typically a non-metal, are attracted and make a really, really strong bond. All of the electrons that are being lost by the metal are being gained by the non-metal in this ionic bond. We also looked at the fact that ionic bonds can be formed between metals that have variable charges, right? Things like iron or copper, right, that make different charges. And we looked at most of them are transition metals. And we also said that ionic bonds can be formed from polyatomic ions, those groups of ions that had an overall charge. And I'm going to remind you that if you haven't been working on memorizing the ions with variable charges and the polyatomic ions, you need to get on that because you really, really will need them when it comes to quizzes and tests. Today, our focus is going to be on molecular compounds, one that are formed by a covalent bond when nonmetals share electrons. We're also going to look at how to tell whether something is ionically bonded or covalently bonded just by looking at the name or the chemical formula. And then we'll wrap up today by learning how to name and write the formulas for acids. So lots to cover today. Let's get started. All right, so like I said, last time we looked at ionic compounds. Today we are going to look at molecular compounds. And molecular compounds contain two or more nonmetals that form a covalent bond. Remember, ionic bonds were formed between a metal and a nonmetal. This is all just nonmetals that are forming this covalent bond. And in this covalent bond, electrons are being shared by the nonmetals. Whereas in an ionic bond, they were transferred. Remember, in ionic, one atom was losing electrons and the other was gaining them. So there was a transfer of electrons. In a covalent bond, these electrons are being shared by the nonmetals in order to get stability. And by stability, I mean 8 valence electrons. Okay? When two or more atoms share electrons in these covalent bonds, they form a molecule. Okay, so molecules are the smallest individual unit of a compound that's formed by two or more atoms. So this would be like H2O, right? That would be a water molecule. And usually we use this term molecule for things that are covalently bonded, so things that are made of all nonmetals. We don't usually use this term for things that are ionically bonded. Instead, we call those formula units. So this term molecule is typically used for things that are covalently bonded. So when we have this molecule, molecules always contain two or more elements that are chemically combined in what's called a definite proportion by mass, which means that every single time you have a molecule of water, for every 2 grams of hydrogen, you are going to have 16 grams of oxygen. They are always in the same proportion by mass. So this is called the law of definite composition. All water molecules will always have this 2 to 16 or 1 to 8 ratio of hydrogen to oxygen. You can think about it a little bit more simply in that all water molecules always have this same ratio of H2O, right? If it's H2O, it's always water. No matter if you have a tiny glass of water or an entire ocean of water, right? If it's water, its formula will always be H2O. It's always going to have that same composition by mass. Okay, so that's the law of definite composition. Essentially, water will always be water. It's always going to be 2 hydrogens and 1 oxygen. If it's a different composition, let's say H2O2, it has a different ratio by mass. Do you see these percentages changed? So H2O2 is called hydrogen peroxide. Okay, it has, instead of having a 2 to 1 ratio of hydrogen to oxygen, it has a 2 to 2, or you can think of it as being a 1 to 1, right? This proportion changes. So if it's a 2 to 1 ratio, it's water. If it's a 2 to 2 ratio, it's hydrogen peroxide. So the law of definite composition states that water will always be H2O. Hydrogen peroxide will always be H2O2. Okay, they have the same elements in the same proportion by mass, no matter if it's, like I said, a small glass of water, an entire ocean of water, or if it's water being produced from a chemical reaction. If it's water, it's always going to be the same proportion by mass. The law of multiple proportions states, though, that our elements can combine in different ratios, like we saw in the previous slide, to make different compounds, right? If we have H2O, then we know that this is water, right? That 2-to-1 ratio. But if it becomes a 1-to-1 ratio, then it's hydrogen peroxide. So the law of multiple proportions states that you can have the same elements that combine in different proportions to make different compounds. Okay, so people get these kind of mixed up. The law of definite proportions states that water is always H2O, hydrogen peroxide always H2O2. No matter how much of these you have, these are always going to be water is H2O, hydrogen peroxide H2O2. The law of multiple proportions states that, okay, if you have some hydrogen atoms and some oxygen atoms, you can combine them in different ratios to make different things. So if we combine them in a 2-to-1 ratio, we can make water. If we combine them in a 1-to-1 or 2-to-2 ratio, we can make hydrogen peroxide. So I know that's a little bit confusing. So like this is another example of the law of multiple proportions. Like if we have copper and chlorine, we can combine them in a 1-to-1 ratio and make copper 1 chloride, or we can combine them in a 1-to-2 ratio and make copper 2 chloride. Okay, so that's the law of multiple proportions. States that we can have the same atoms combined in different ratios to make different compounds. Okay, so I know those laws sound pretty similar, but there are differences. The law of definite proportions says that water is always H2O2. The law of multiple proportions says that H and O can be combined in different ratios to make different things. All right, now let's go ahead and look at how these covalent bonds between nonmetals are formed. Like I said, in a covalent bond, these two atoms are going to share a pair of electrons. So remember, everybody's trying to get 8, right? That was the goal. So if we have two different nonmetals that have 7 valence electrons, like let's say this is fluorine. Fluorine has 7 valence electrons. So here's our valence electrons for fluorine. So there's one. Here's the other one. Okay, each one of those has 7. So fluorine is very reactive because it has 7 valence electrons, and it has a high electron affinity. It really wants to gain another electron. So what happens is that when two fluorine atoms come near each other, they actually share these electrons. So now the fluorine on the left has 2, 4, 6, 8, and the fluorine on the right also has 2, 4, 6, 8, right? And so by sharing these electrons, each one of the elements actually gets an octet. So instead of ionic compounds where we're seeing that transfer of electrons, in a covalent bond, they're sharing the electrons so that they both end up with this octet. Okay, remember, the name of the game is to always get 8 valence electrons in bonding. So here's some common molecular compounds that you've come across just in general. So water is one of them. We've been talking about water a lot, but another one is carbon dioxide. That is made up of all nonmetals. Anytime you see a formula that has all nonmetals, it's going to be made up of covalent bonds, so we call it a molecular compound. So all of these, all nonmetals. So carbon dioxide is used in fire extinguishers, dry ice, which is really fun, your carbonated sodas, right? We have, sulfur dioxide is used in preserving fruits, which is really common around here, and also vegetables. It's used as a disinfectant in some breweries, which is interesting. And so we've got, a lot of molecular compounds that are used very, very commonly. So here's our rules for naming molecular compounds. They're actually really similar to the rules we've already used for naming ionic compounds, except we are going to use prefixes. Okay, so whenever you think about naming molecular compounds, I want you to think about prefixes. Okay, and I'll show you what I mean by that in a minute. But the first element is going to be named using the name from the periodic table, just like we've done before, and a prefix. The only exception to this rule is if you just have one of the first element, don't use mono. Okay, and we're going to go through lots of examples, but just don't use mono for the first element. I want you to remember that. And then the second element, we're again going to change to end in IDE, just like we've done before. Okay, so the first element stays the same, the second element changes to end in IDE, and for both of them, we're going to use prefixes. So here's the prefixes. So the prefixes are mostly what you've seen in math. Like hexa means 6, so a hexagon has 6 sides. Or penta means 5, so pentagon has 5 sides, right? A lot of these you may have seen before in math class. Some of the early ones you may not have seen, but you do need to commit these to memory and memorize them as soon as you can so that you'll be able to name these molecular compounds. Likely, though, you're going to do enough practice with these that you'll kind of accidentally memorize them along the way. So let's go ahead and do some examples. So we're going to name this compound. So the name of the first element will stay the same. The name of the second element will change to end in IDE, just like we've done before. But now we are going to use prefixes to talk about these subscripts. So if you'll recall, when we did ionic compounds, I said it doesn't matter what the numbers at the bottom are when we're naming things, right? That's for ionic. When we're doing molecular compounds, though, it does matter what those numbers at the bottom are, and we're going to use prefixes to say what they are. So like in this molecule, do you see that there's P2? So we're going to call this diphosphorus. Because if we look on the previous slide, our prefix for 2 is di. Okay, so we're going to call this diphosphorus. And then we have 5 oxygens, right? So we'll say pentoxide. If you look again at the previous slide, we'll see our prefix for 5 is penta. Okay, so that's where we're getting that pent from. And so a lot of people will actually write pentaoxide, and that's actually not quite right. Whenever we use oxide, we actually drop the end of the prefix. So this becomes pentoxide, which I know is a little bit confusing. But if you leave the A in there for this class, I won't mark you wrong, but do try and take it out if you can. And higher levels of chemistry, you may get dinged if you leave that A in there, so it's important to build good habits. But right now I want you to focus on getting the right prefix. So this is called diphosphorus, right? P2 is diphosphorus pentoxide to represent the 5 oxygens. And here's my little note about the A's and the O's. Let's try another one. So CCl4. So the first one is carbon. The only time we don't use a prefix in molecular compounds is when there's just one of the first element. Do you see that there's just one carbon here? So we don't use a prefix. We're just going to say carbon. We don't need mono for the first element. And in fact, you will get marked wrong if you include it, so be careful. And then there are 4 chlorines, so we call that tetrachloride. So this is carbon tetrachloride. So 1 carbon, 4 chlorines, carbon tetrachloride. My example, if you ever forget, let's think about CO2. Most of us know CO2 is carbon dioxide. This is a molecular compound. It's made up of all nonmetals, and it follows that naming system we were just talking about. This is carbon, and we don't use mono for the first element. Even though there's just one, right, we don't use mono for the first element. But there's 2 oxygens, so we call this dioxide. So you're actually familiar with this naming system, even though you don't know it, right? So again, no mono for the first element, but otherwise always use a prefix. So let's try these out. I want you to try to name these using these prefixes. I've included them over there on the right. But again, you should commit them to memory as soon as you can. But for now, go ahead and use them. So go ahead, name these compounds, and then come back when you're ready to see the answers. All right, so for this first one, we have just 1 nitrogen, right? So we'll use nitrogen dioxide, right? So 1 nitrogen, no mono here, because we don't use mono just for the first element. And there's 2 oxygens, so that's dioxide. Same thing for the next one. So it's silicon, again, no mono, just silicon, and then there's 4 fluorines, so we call that tetrafluoride. So now on the next one, we do have 2 of the first element, so we do need to include a prefix. The only time we don't have a prefix on the first element is if there's just one. But if there's two, we do need a prefix. So this will be dinitrogen, and then 6 fluorines is hexafluoride. On to the next one, just one of the first elements, so we just put carbon, and then 4 bromines, so tetrabromide. Just one of the first elements, so no mono, we just write nitrogen, and then 3 chlorines, trichloride. So I think for the most part, this isn't too tricky as long as you know those prefixes. As soon as you know the prefixes, this becomes really straightforward. We can also do this the other way around. We can take the name and write the formula. When we did this for ionic bonding, we had to go through and write the ions and circle and switch and all of that, right? And it gets a little bit tricky, especially if you don't have all of those ions memorized. For molecular compounds, right, these covalent bonds, this is actually really easy. All we're going to do is use the prefix to tell us how many of each element we have. So like this one, diphosphorus tells us we have 2 phosphorus. So this becomes P2. And then trisulfide tells us we have 3 sulfurs. So this is S3. There's no circling and switching, no nothing. You're just going to take the prefix and use that to tell you how many of each element you have in your compound. So this next one, this is nitrogen. There's no prefix, so that tells us there's just one. Dioxide, so that tells us 2 oxygens, so O2. For the next one, we just have phosphorus, so no prefix, that tells us just one. Pentafluoride tells us 5 fluorines. No prefix on nitrogen, so that's just nitrogen. And then mono tells us there's just 1 oxygen. So there you go. On this last one, again, no prefix on silicon, so it's just Si. And then hexa tells us there's 6 chlorines. So it's Cl6. Okay, so hopefully this is really straightforward. For when we're writing the formulas, we're just going to use our prefix to tell us how many of each element there are. I think you should be happy when you come across these molecular compounds because they tend to be easier than our ionic compounds. All right, let's go ahead and get some practice on this. Do problems number 25 to 26 on the Chapter 3 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so usually what I have found is that when we're doing ionic bonding, people can get really good at that with the circling and switching and all of that, and they get solid at ionic compounds. And then when we do these covalent bonds and the molecular compounds, people get really good at those and can definitely do that. The problem comes when I start to mix them up and people start to be confused about, okay, is this ionic bonding? Is it covalent bonding? How do I name it? How do I know? Right? Remember, ionic bonds are always going to be formed from the transfer of electrons. So a metal to a nonmetal, right? That metal cation loses electrons and gives it to the nonmetal so that each of them can have 8 valence electrons. Whereas covalent bonds are always going to be formed between 2 nonmetals sharing their electrons. So one of the easy ways to see the differences here is that when you have an ionic bond, you have a metal and a nonmetal, right? One of each. Whereas if it's a covalent bond, where a molecular compound, you have 2 nonmetals. Okay, so that's going to be the difference. A metal and a nonmetal is ionic, whereas 2 nonmetals is going to be covalent. So here is a nice summary of how to name everything. I gave you this bit over here, this ionic stuff, last time, right, for how to name ionic compounds. But now, today, we talked about how to name molecular. Okay, so remember, if you have an ionic compound, it'll be between a metal and a nonmetal, or a metal and some polyatomic ion, whereas molecular is going to be between 2 nonmetals. So if you see your formula has a metal, automatically it's going to be ionic, because that's the only one that has a metal in it. But if it's got 2 nonmetals, then you go molecular. So that's how we'll tell the difference. So let's practice this. So this says, name each of the following ionic or molecular compounds. So we're going to name these. The first thing we need to do is figure out, is it ionic or is it molecular, right? Okay, so let's look at this first one. So this is going to be easier if you have a periodic table in front of you, so you can figure out whether things are metals or nonmetals. You should have colored this in earlier in the course when we covered all of that. But if you haven't, now's a good time to go through and shade the metals and the nonmetals so you know which is which. If you haven't shaded it though, the ones on the left-hand side of the periodic table tend to be metals, and the ones on the right-hand side of the periodic table tend to be nonmetals. All right, so looking at this, we have boron and fluorine. Both of these are nonmetals, right? Boron's a nonmetal, fluorine's a nonmetal. So when we name this, this is going to be molecular. Oops, my apologies. So this is molecular. So when we have a molecular compound, now we are going to follow the prefixes, right? So whenever you think of molecular, I want you to think prefixes, okay? So prefixes, therefore, we're going to name the first one as boron. Since there's only one of that first element, we don't need a prefix. But then we're going to use a prefix for the second one, right? There's 3 fluorines, so we call this trifluoride. Okay, so again, this was all nonmetals, so it's molecular, so we need prefixes. So you get boron trifluoride. Let's try the next one. Oxygen and chlorine. So both of those are nonmetals, so this one is also molecular. So we're also going to use prefixes. Okay, so if it's all nonmetals, it's molecular, use prefixes. So again, there's only one of the first element, so we'll write just oxygen and move on. Okay, but there are 2 chlorines, so we call this dichloride. All right. On to the next one. So now we see aluminum and oxygen. Aluminum is a metal and oxygen is a nonmetal. Okay, so since we have a metal and a nonmetal, this is ionic. So anytime we have ionic, I want you to think no prefixes. Okay, when it's ionic, we're just going to write the names of the elements, and change the second one to end in IDE. So this will be aluminum oxide. So again, no prefixes because this one is ionic. We only use prefixes for molecular. Okay, and we don't use a Roman numeral here because aluminum only makes one ion. Aluminum is always a 3+, so we don't include a Roman numeral. We'll only use that for elements that form more than one charge. All right, on to the next one. So this is nickel and phosphorus. So again, nickel is a metal, so we know this is ionic, so no prefixes. Okay, no prefixes for ionic compounds. However, nickel is one of those elements that's a transition metal, right? It's in the middle. So we need to figure out the charge on nickel. So this is going to be nickel something, right? And we need to include a Roman numeral because nickel has a variable charge. And then this last bit, PO4, that's a polyatomic ion. So we're going to look up what PO4 is, right? And we're going to see, oh, that's phosphate. And hopefully you already have these polyatomic ions memorized because you are on your game. But if you don't, remember that the polyatomic ions can be found on that ions to be memorized list. But you're not going to have that list available to you on upcoming quizzes and tests, so make sure to memorize those as soon as you can. All right, so our last thing we need to do is figure out the charge on nickel. Okay, so remember, the way that we figure out these charges is we kind of uncircle and switch. So this 3 here, that 3 showed up because phosphate is PO4 3-. That's where that 3 came from. Do you see that there's nothing out here? Like the phosphate is not in parentheses? That means that the nickel was just a 1+ charge. Because if it was a 2+, there would be parentheses around that phosphate and the 2 would be on the outside. But since there's no parentheses there, we know that nickel was just a 1+. So this is nickel 1 phosphate. Okay, so like I said, part of the challenge here is to figure out whether something is ionic or molecular. And then once you figure out whether something's ionic or molecular, you need to follow the rules for that classification. Okay, so there you go. Let's try now writing the formula for these. Okay, the first one is aluminum chloride. So again, we see aluminum, that's a metal, right? So this is a metal and a nonmetal. Anytime we have a metal and a nonmetal, that's going to be ionic. Okay, when you see an ionic compound, I want you to think, ionic compounds are made from ions. Therefore, we need to circle and switch. Okay, so we'll write out our ions because this is an ionic compound. So aluminum is a 3+, and chlorine is just a minus charge. So then we take our 3, that's going to go to the chlorine, and we get AlCl3. Okay, all right, on to the next one. Phosphorus pentabromide. So phosphorus is a nonmetal, and bromine is a nonmetal as well. So this is going to be molecular. Okay, also, do you see that there's a prefix here? Right, anytime you see prefixes, that's going to indicate that's also a molecular compound because we only use prefixes with molecular compounds. Okay, but the fact that this is 2 nonmetals also tells us it's molecular. So when it's molecular, we don't write out the ions. No circling and switching. We're just going to use the prefixes to tell us what the formula is. So since there's no prefix in front of phosphorus, we know there's just one phosphorus. But since there is a prefix in front of bromine, we use that, so that's 5 bromines. So that's Br5. Okay, let's try the next one. Cobalt is a metal, and our nitrate is a polyatomic. Okay, anytime we see a metal, we automatically know that that is an ionic compound because that's the only type of compound that metals form. So anytime we see ionic, right, we need to think, ionic compounds are made from ions. I need to write out my ions and circle and switch. So cobalt is one of those metals in the middle that forms ions of variable charge. So it includes a Roman numeral to tell you which charge to use. So that's actually easy, right? We see cobalt 2, that's telling us cobalt is a 2+. And then nitrate is a polyatomic ion, so we just look at that chart and we see nitrate is NO3-. Okay, so now these are not equal and opposites, we have to circle and switch. So the 2 goes to the nitrate, right? So this is CO, and then again, remember that polyatomic, that entire thing needs to go in parentheses. So we get NO3, and that 2 will go on the outside of the parentheses to say we need 2 of that entire nitrate. All right, last one, we see dinitrogen pentoxide. So nitrogen is a nonmetal and oxygen is a nonmetal. So this is going to be molecular. But again, we could have known that anyways because we see these prefixes. Anytime we see prefixes, we recognize that as molecular because that's the only one that uses prefixes. So now we're just going to use the prefixes to tell how many of each one. So dinitrogen tells us 2 nitrogen, so N2. And then pentoxide tells us 5 oxygens, so O5. Okay, so again, in order to do this part, you need to be really solid at ionic bonding and really solid at molecular stuff so that when you get here, you can tell the difference between them and then follow the rules for each one of those naming systems or for forming the compounds. Okay, this starts to get tricky if you're not solid on all of it before you get going. So make sure to get a lot of practice in to feel confident going into the quizzes and tests. All right, let's go ahead and get some practice. So we're going to do problems number 27 through 30 on the Chapter 3 lecture worksheet. Remember, the answer key is posted, so please check your work as you go. I would hate for you to get all the way through this and realize you're doing it all wrong. Also, if you get stuck, the answer key is a really valuable tool for helping you learn how to do it, right? So what I recommend is maybe do it once with the help of the answer key, and then print out another one and do it again on your own to make sure you're really solid on how to do all of this nomenclature. So go ahead, pause here, work on these problems, and then come back when you're ready to move forward. All right, our last type of compound that we're going to learn to name are acids. Okay, acids follow a bit of a different rule. Acids are actually made for all nonmetals, but we actually treat them like they're ionic compounds, which is a little bit weird. So they follow a whole different naming system that's just for acids. Okay? Acids can be recognized because they are always going to have a hydrogen in the front. So like there's an example, another one would be like H2SO4 or H3PO4. Acids will always have a hydrogen as its first element. Okay, so that's how we'll recognize, oh, we need to name this as an acid because there's hydrogen in the front. So here's our rules for naming binary acids. And by binary acids, I mean it's going to have hydrogen and one other element. So like hydrogen and chlorine or hydrogen and bromine, but just that one other element. Okay, so our first rule is that we're going to use the prefix hydro and then followed by the root of the second element and add ic. So essentially our general formula is it's going to be hydro something ic acid, but it's always going to just change this middle bit here. It's always going to be hydro something ic acid. Like this is a binary acid because it's hydrogen and one other element. Even though there's multiple hydrogens, it's hydrogen and one other element. And in this case, it happens to be sulfur. So we call this hydrosulfuric acid because we're just going to fill in what goes there. Okay, so it's always going to be hydro something ic acid. And that something is going to tell you what the hydrogens are bonded to. Like this one. This one, we have hydrogen and one other element, right? That other element is fluorine, so we say hydrofluoric acid. This one, it's chlorine, so it's hydrochloric acid. Or bromine is hydrobromic acid, and so on. But it's always going to be hydro something ic acid. And you're just going to fill in whatever element that hydrogen is bonded to. Okay, so this is for binary acids. Hydro something ic acid. So like this one, hydrogen and one other element. So this becomes hydro something ic acid, right? And so since it's iodine, hydroiodic acid. Here's another one, hydrogen and one other element. Even though it's, multiple hydrogens, it's still just one other element. So this is selenium, so this is hydroselenic acid. Again, hydrogen and one other element, so it's hydrofluoric acid. So again, all of them are going to be hydro something ic acid. You just need to figure out what goes in that blank. All right, so that's how you name something if you have the formula, but we can also write the formula if we have the name. And what's really important is we are going to treat this just like ionic bonding, but our cation is always going to be hydrogen. We just need to figure out what the anion is. So this hydrobromic acid, that's telling us that it's got bromine in it. So it's hydrogen and bromine bonded together. So again, we're going to have hydrogen as our cation and then bromine as our anion. Do you see that their charges are equal and opposite? They're both 1 plus and 1 minus, right? So they kind of cancel each other out. So no circling and switching necessary. We just put them together. Let's try this one. Hydrophosphoric acid. So this is telling us it's going to be hydrogen and phosphorus. So again, we've got our hydrogen and our phosphorus. These are not equal and opposite though. So when we've got our H plus and our P3 minus, that 3 is going to go to the hydrogen, and we get H3P. So even though these are not ionic compounds, right, they're made from nonmetals, we're going to treat them like ionic compounds when we are doing the formulas. All right, our last type of acid that we're going to name are oxyacids. So the ones before, binary acids, were hydrogen and one other element. But sometimes you'll get oxyacids. And these are just that they also have oxygen. So they'll have hydrogen, another element, and oxygen. Okay? These are usually going to be made from polyatomic ions. So hydrogen is still going to be in the front. That's how we recognize that it's an acid. But now the compound is going to have a polyatomic ion instead of just having one other element. So here's what I want you to remember. If you have an ATE ion, it's going to become an ic acid. If we have an ITE ion, it's going to be an us acid. Okay? The way that I remember this is I ate something icky. So my 8 ions turn into ic acids. I ate something icky. And then I just remember the ites turn to us because I ate something icky. But however you'd like to remember that, okay? The ATE polyatomic ions go to ic acids. The ITE polyatomic ions go to us acids. So let's try this out. So here's one. So this has SO4. You should recognize that as one of our polyatomic ions, SO4 2-. That's sulfate, right? So since we have sulfate, right, I ate something icky. So since this is sulfate, it's going to change to an ic ending. And so this will become sulfuric acid because it's from sulfate. So we're going to change the name of the polyatomic ion. We're going to take off the ATE and we're going to change it to end in ic. So sulfate becomes sulfuric, and then we're going to use the word acid to say there's a hydrogen in the front. Let's try this one. This is another polyatomic ion that we recognize. NO2 is NO2-. That's nitrite. Remember that ite polyatomic ions turn into us acids. So nitrite, we change it to end in OUS, so this becomes nitrous acid. So they're all going to end in the word acid because they're acids, but the 8 polyatomics go to ic, whereas the ite polyatomics go to us. And then, lastly, writing the formula for these oxyacids is, again, we're going to treat them like ionic compounds. We are going to write out the ions, circle and switch. Remember, our cation is always going to be hydrogen because these are acids. So, like this one, phosphoric acid. Do you see this is an ic acid? That means it came from an 8 polyatomic ion. So phosphoric acid came from phosphate, PO4 3-. Okay, so we're going to write out our ion. So it's always going to be hydrogen as our cation. And then we have our phosphate as our anion. And so we'll circle and switch. H+, PO4 3-. This 3 is going to go to hydrogen. So we get H3PO4. And then we have sulfurous acid. Remember, the us acids came from ITE polyatomic ions. So sulfurous acid came from sulfite. Okay? So again, hydrogen is our cation because it's an acid. So we have H+ and SO3 2-. So that 2 is going to go to the hydrogen when we circle and switch, and we get H2SO3. So again, it's really important that you know polyatomic ions when you're naming these oxyacids so that you can recognize them in a formula or know what polyatomic ion they came from. Alrighty, now we can go ahead and do problems number 31 to 32 on the Chapter 3 lecture worksheet. And this actually wraps up our chapter on nomenclature. Okay, I have this flow chart, which I think is really handy for all of the different types of nomenclature. So it talks about how to name things if it's an ionic compound, a molecular compound, or an acid. So you can print out this slide, or I have this flow chart available to you in Canvas in that Chapter 3 module. This is going to be really, really helpful when you're learning how to name these formulas because I know there's a lot going on. This requires a lot of practice to keep all of these straight. Don't think you're going to get it on the first time through. It requires a lot of practice for everyone because it's a new system of nomenclature. Okay, but like I said, one of the biggest challenges is figuring out, is something an ionic compound, a molecular compound, or is it an acid? Because people can usually do it. Like if I said it's ionic, you know all the rules that go with ionic, or you know all the rules that go with molecular, right? But the tricky part is determining what it is and then how to name it or to write the formula from there. So make sure you are getting a lot of practice on this stuff. That's the way to get good at it. So like I said, I would do this chapter 3 lecture worksheet once, check your work with the answer key, and then print it out and do it again, because the more practice you can get, the better you will be at it, especially when it comes to, memorizing those ions of variable charges, the polyatomic ions, and those prefixes for molecular compounds. So get lots of practice on this and ask me any questions at all that you have. I'm more than happy to help if you're getting stuck. But otherwise, you got to just keep working hard, keep practicing, and I will talk to you guys next time.